In section 2, we are going to focus on exponential functions. So to start off, we're going to define what an exponential equation is. So it is an equation where the variable appears as an exponent. So the most general form is y equals a to the x, where a is your base. And that's kind of what determines whether or not you're looking at exponential growth or exponential decay. So if your base, which is a, is greater than 1, then we are looking at exponential growth. If a is between 0 and 1, we are looking at exponential decay. So a couple things about a, it cannot be negative. So there can be a negative in front of it, but when we're talking about the actual number that's raised to an exponent, it has to be positive. So when it comes to kind of like the typical graph, so exponential growth, you start off with smaller values, and as x increases, so does your graph. For decay, it then works the exact opposite way. For smaller values of x, you're looking at a larger graph, and as x increases, it gets smaller. And that's kind of what exponential growth and decay looks like. So in our first second examples, we're going to determine if the equation represents an exponential function or not, and if it does, is it a growth or decay function? So we have y equals 4 to the x. So does our variable appear as an exponent? Yes. So this is an exponential function. My second question, is this growth or decay? So my base is 4. 4 is bigger than 1, so it is growth. Okay. Our second example, we have y equals 3x squared. So in this case, my variable is not an exponent. So this is not exponential. This is actually an example of a quadratic, which is what we talked about in section 1. Next, we have y equals 6x plus 7. Also not an exponential because our variable does not appear as an exponent. This is a linear equation. And then our last one, y equals 1/3 to the x. So this is exponential. My variable is an exponent. 1/3 is between 0 and 1, so it represents decay. So there are quite a few types of applications that we're going to be looking at for exponential functions. So bacteria growth or decay, percent growth decay, population growth or decay, they can all be modeled by exponential equations. So when we're talking about general growth or decay, we use the equation y equals a parentheses 1 plus or minus r to the x. So in this case, our final amount is represented by our variable a. Our initial amount is represented by a. Our growth or decay rate is r as a decimal. So if you're trying to figure out in this case whether or not you have growth or decay, growth, you would use 1 plus r in the parentheses, and if you're looking at decay, you use 1 minus r. And then the time that we're looking at is x. So our variable x here always represents a time. Another very common occurrence is in science. So anytime you have half-life, radioactive decay, those are modeled using an exponential equation. So that exponential equation is a equals a naught times 1/2 to the t over h. So in this case, our final amount is represented by a. Our initial amount is a naught, so it's just saying what did you start with. Our half-life is h, and our time is t. The last one we're going to focus on is compound interest and continuously compounded interest. So compound interest is modeled by the equation A equals P times 1 plus R over N to the NT. So our final amount is A. Our initial amount is P. It's also referred to as a principal amount. That's where the P comes from because it's actually referred to as a principal amount. Our interest rate is written as a decimal, so that's R. The number of times interest is compounded in 1 year is N. And then our time for compound interest is always in years, and that's our variable T. So in the other two, time can be whatever variable in whatever time, whatever measurement we want. Seconds, hours, minutes, days, weeks, years, months, whatever measurement you can think of. But when we're talking about compound interest and continuously compounded interest, time is always in years. So for continuously compounded interest, that formula changes slightly. It's A equals PE to the RT. So our final amount is still A, our initial amount is still P, which is still a principal, our interest rate as a decimal is still R, and our time in years is T. So we're going to kind of do an example of each of these equations we've talked about so you can see how they're used. So we'll set up the exponential equation that represents the scenario, and then we'll use it to solve for a final amount. In our first example, we have that the population of a certain animal species decreases at a rate of 3.5% per year. You have counted 80 of the animals in the habitat that you are studying. Write a function that models the change in the animal population and determine how many animals there will be in 10 years. So first thing I need to identify, this is one of my general exponential growth or decay problems. So I first need to determine if I'm looking at growth or decay. And the word decreases here kind of lends me to know that I'm talking about decay. So I'm going to use the equation y equals a times 1 minus r to the x. So for my equation, I'm going to only plug in a and r. So an equation does not have a value plugged in for x yet. So I have y equals my initial amount, 80, and then 1 minus my decay rate at this point, 3.5% as a decimal, which is going to be 0.035 to the x. I can simplify that. I can actually go ahead and do the 1 minus 0.035 so that I can just write it as a single value in my decimal, which is 0.965 to the x. So this way I can identify this equation as decay because my base number, 0.965, is between 0 and 1, so I know it's decay. So the second half of the problem is determine how many animals there will be in 10 years. So now I'm going to plug in a value for x. So I'm going to do 80 times 0.965 to the 10th. And I want to plug this into my calculator as exactly as it appears. I'm not going to do it in steps. I'm going to type it exactly like that. And I'm going to get 40.85. Now, because we're talking about animals here, living things, I do want to round up to a whole number. I typed my equation wrong. Give me 1 second. So it should actually be 52.02. So I do want to round that to a whole number. Sorry, 56.02. So do round that to a whole number, which is going to be 56 animals. Other times we'll leave our answers as decimals. It really is dependent on the situation. But if you're talking about a person or an animal, something that is living, we typically round to a whole number. Our second example says that the world population in 2000 was approximately 6.08 billion. The annual rate of increase was about 1.26%. Write the function that models this scenario if the growth rate remains constant. And then we're actually not going to predict the world population for 2022. We're going to predict it for 2025, since 2022 is in the past. So this is an example of general exponential growth because we are increasing our Great, so I'm going to use y equals a times 1 plus r to the x. So for my initial amount, I'm going to leave it as 6.08. I'm not going to write out all of the zeros that are associated with a billion. And then it'll be 1 plus, and then 1.26% as a decimal is 0.0126 to the x, which if I simplify my parentheses comes 6.08 times 1.0126 to the x. Now I want to predict the world population for 2025. So I'm not going to actually plug in 2025 for x, because my initial equation is based off what the world population is in 2000. So x here is actually the number of years since 2000. So I'm actually going to be plugging in 25. So I'll have 6.08 times 1.0126, and then my exponent is going to be 25. Here, I'm going to leave it as a decimal. So I'm going to have 8.31 billion. Because I'm talking about number of people, and in this case, since my decimal isn't just like 8.31 people, it represents a number of people in terms of billion. So I can have a decimal here. So it'd be approximately 8.31 billion. Okay. Next, we have that a new truck that sells for $29,000 depreciates 12% each year. Write a function that models the value of the truck and find the value of the truck after 7 years. So depreciates is kind of my key term here, and that does mean lose value. So it is going to be decay, so 1 minus r to the x. So I have y equals 29,000 times 1 minus 0.12 to the x, which becomes 29,000 times 0.88 to the x. So when it comes to finding my value of the truck after 7 years, I'm going to plug in 7 for x, so 29,000 times 0.88 to the 7th. When it comes to a problem like this where I'm dealing with money, my final answer should always be rounded to 2 decimal places. So my price is going to be 11,851 and 59 cents. So anytime we're dealing with money, always round 2 decimal places unless you are told otherwise. So those were kind of examples of some general exponential growth or decay problems we might see. Now we're going to look at an half-life example. So we have that arsenic 74 is used to locate brain tumors. It has a half-life of 17.5 days. Write an equation to represent this problem, and then we're going to find the amount remaining after 6 days from a 90 milligram sample. So for my equation, 90 is my initial amount. So I'll have 90 times 1/2, and then my exponent is going to be my time t over my half-life, which is 17.5. So the important thing here when we're talking about half-life is that your half-life units and the time units that you're solving for or plugging in have to match. So if my half-life is in days and I want to find a remaining amount after a certain amount of time, that time has to be in days as well. So they do have to match in that aspect. So now when I plug in, I'm going to do 90 times 1/2, and then my exponent is going to be 6 over 17.5. Again, I'm going to type this exactly as it appears in my calculator, and I'm going to get a final amount of 70.96 milligrams. So when we're talking about half-life and we're talking about elements and whatnot, we want to round 2 decimals, but we also need to make sure that we have units. So far in every problem I've done, when I get to my final answer, I've had units on it. So for 56 animals, 8.31 billion, my dollar sign, my milligrams here. So it is very important that when you are doing problems or application problems with exponentials, your final answer does contain variables. Okay, so last two examples are going to be our exponential, our compound interest, and our continuously compounded interest. So in our first example, we have that you deposit $1,200 into an account yielding 2% interest compounded monthly. Write the equation that represents this situation, then determine how much money is in the account after 10 years. So you have to decide whenever you look at compound or continuously compounded interest, whether or not which equation you're going to be used. So in this case, it tells me that interest is compounded monthly. So this is my general compound interest equation. So it's going to be A equals P times 1 plus R over N to the NT. So I'm going to plug in values for P, R, and N, and I'm going to leave T as my variable. So my initial amount, $1,200. Then I'm going to have 1 plus R is 2%, so 0.02. N is the number of times interest is compounded in a year. So it says here that interest is compounded monthly, and there are 12 months in a year. So my denominator is going to be 12, and then my exponent is going to be 12t. Now, unlike the previous examples where I simplified what was in the parentheses, I'm not actually going to do that for compound interest. And the reason is R over N is not necessarily going to be a nice decimal. It may terminate, it may be really long. So I always just leave it in that form when I'm plugging in, and then that way I don't have to worry about rounding at any point. So now I want to find how much money is in the account after 10 years. So I'm going to do 1,200 times 1 plus 0.02 over 12. And then my exponent is going to be 12 times 10. So just like with my other problems, I type that into my calculator and I'll get $1,465.44. So again, always rounding 2 decimals because we are looking at money. Last example, we're going to have the same situation, but in this case, we are going to compound interest continuously. So the only thing that changes the equation that I use. So this time I'm going to be using my A equals PE to the RT. It also allows me to kind of make a comparison between which one is better. So I'm going to have A equals 1,200 E, and then my exponent is 0.02 T. So now if I want the amount after 10 years, 1,200 times E, and my exponent 0.02 times 10. Now E is technically a number. There is a button on your calculator that will give you E. So if you need help finding it, just let me know, but E is a number. So I type it into my calculator. I get my final amount is $1,465.68. So I can see here comparing it to my compounded monthly, not a huge difference, only like 16 cents separates me between compounded monthly and compounded and interest compounded continuously. So not a huge difference. It's not always the case. It really depends on how much you're initially depositing, when interest is being compounded for the general compound interest equation, and then how much time you're looking at. So last thing I want to include in the notes are some common values for N for our compound interest formula. So N values for compound interest. So there are a few ones that you're going to see pretty frequently. So one of them is going to be yearly, which in that case, N equals 1. Once a year happens once a year. We'll have monthly, like we just saw, in which case N is 12. We can see quarterly, in which case N is 4. Semi-annually, which is when n equals 2. Daily, in which case n equals 365. And not very often, but on occasion, you might see weekly, in which case n is 52. That's probably the most rare one we're going to see, is the weekly, but the other one's very common. Other than another word for yearly is you might see annually. Those mean the same thing. So annually, yearly, those are both one. So if you have any questions about any of the equations that we discussed for exponential functions, whether it was our general exponential growth, half-life / radioactive decay, or even the compound interest formulas, please let me know.